up to this point in the class, our focus has been on these two equations here, which we even sort of organized and numbered here as equation number 1 and equation number 2. They relate the current or initial position of the object, there's x naught and there's v naught, initial speed, with what the position and the speed of the object would be some delta t later in time. What we need to look at now is, and think a little bit about, is where do these a's come from? Where do these accelerations come from when we were working with these equations? If you're doing problems out of the book, sometimes the equation was just given. You might have been given a car that had some acceleration of 2 meters per second squared, maybe minus 1 meter per second squared. Sometimes the numbers were just given for A. They were just given. Other times we knew some information, say, about the Earth, where this was the equation dealing with the y coordinate, maybe y and v sub y. Then the A would have been something like minus g, which is minus 9.8 meters per second squared. So there was at least one case where the A was sort of constrained to something about property of the Earth or something that you might know about. But by and large, the acceleration of those equations there was just about anything you wanted it to be. In this unit of the course, though, we're going to move on a bit and see where maybe that acceleration might come from. And in particular, I just want to start you out with the sort of the message in here, or the mantra for this part of the course here, that really for us the accelerations will come from forces. This is sort of our phrase for the class. Accelerations come from forces. So we're really not free just to choose the 2 and the minus 1 and the 9.8. So like if a car had an acceleration of 2 meters per second, that might have come from a braking force. Or if something falling off a building or falling down had an acceleration of minus 1 meters per second squared, that would have had something to do with maybe air drag in combination with gravity or something like that. Even the 9.8 that we know is the acceleration for something falling near the Earth has to do with the force due to gravity. So our new phrase, or as we move on and get a little more sophisticated in this class here, we're just going to start saying that accelerations come from forces. Let me try to convince you of some new way of thinking about this. So probably the most famous law in physics that everyone knows about is F equals to ma. But one of my claims or my messages to you, at least in this video and as we go into this next section of the class, is this really is true, but it's not really the best form to remember. In fact, it's probably one of the most unhelpful forms of Newton's law that I can possibly think of here. F is equal to ma, but it doesn't help you very much. Let's see why not. So suppose you have some floor like this, and maybe you have a box here, and the box is being pulled on maybe. Some child has a rope or something, but in either case the box is experiencing some force F to the right there. And a new parameter for us here will be the mass of the box. We'll just call it the symbol m, so say the box has some mass. We'll talk more about mass later, but for now mass is sort of the amount of stuff that the box is made out of. So you took all the little atoms or molecules or whatever you think of a box being made out of, an atom altogether, that would be the mass of the object. So the question then is, how is this box going to move? Say if it's sitting here at rest or not at rest or whatever the case may be. How is this force going to affect its motion? Well, my claim is that you can write down this very famous law here of Newton's F equals ma and maybe look at it and go, well, I have a force, I have a mass, maybe I can get an A from it. But my claim is that it's actually much easier to write from the onset that F is just A is equal to F over m. I think this is a much more useful form of Newton's law. So once again, we'll just cross out the F equals ma, and I think we'll just stick with A as F over m. Why? Because what I can do now is I can look at the box and say if this force here happened to be something like maybe a 2 Newton force. So the child is pulling on the box with a force of 2 newtons, and maybe this mass came in to be 1 kilogram, something like that. Well, if that happened then, if you're sort of using A is equal to F over m, then the acceleration on the box will just be 2 newtons divided by 1 kilogram, and so the acceleration on this box here then would be 2 meters per second squared. So why is this so useful? Well, it's an acceleration that clearly came from a force now. We weren't free just to choose any acceleration we wanted for the box. It came from the fact that some child is pulling on it with a force of 2 newtons, and the box has a property called mass of 1 kilogram, so the acceleration on it must be 2 meters per second squared. What can you do with the 2 meters per second squared? Well, this is the A now that you could conceivably plug into one of these equations that we've been dealing with for a while now. This acceleration would be the acceleration that would go right in there for predicting the new position of the box. Or it would be the acceleration that would go into this equation here for predicting what the new speed of the box would be. So see, the equations of motion are still useful, they're still correct. It's just that we're no longer free to choose any old A we want anymore, or a number for A that comes from a problem has to have some interpretation. So in this case now, the interpretation of where did the A come from? Well, like I said, accelerations come from forces. It was because a 2 Newton force was applied to a 1 kilogram box We got an acceleration of 2 meters per second squared. Now we're free to go back to the original equations that we're used to predict where the object's motion is going to be. Where is it going to be some dt in the future, and what speed will it have? But my claim is, as I keep going on here, is that this form of Newton's law isn't the most useful one either. Let's see why. Let's go back to a box then. So here's that same box on a flat surface, and let's say there's a force pulling this way. Say a force 1 or maybe 2 newtons. So the same child pulling that way with 2 newtons. And let's say back this way, someone else is pulling on the box, maybe another kid with a force of 5 newtons. So I think you can tell sort of intuitively that there is sort of a so-called net force. A net force on this block here, and without really doing anything too sophisticated, you can tell that it's going to be 3 newtons to the left. But really what you did to get the 3 newtons to the left is you added these forces together. You said, hey, somebody's pulling to the right with 2 newtons, to the left with 5 newtons. And if we stick with our usual sign convention that everything to the right is positive and everything to the left is negative, everything to the left is negative then really what we have is a sum of forces here. We have a sum of forces which says we have a plus 2 newtons to the right plus a minus 5 newtons to the left, and that equals a total force of 3 newtons because 2 plus negative 5 is minus 3. So we have a net force of 3 newtons to the left. That's what the minus sign means right here. The net force is actually to the left. So we'd expect then that all told there's sort of a leftwards force in this box. But hopefully you can see now why F equals ma isn't really that useful here, but now neither either is F over m. Because this F over m equation, even this one for that matter, seems to imply that there's only one force on the object, but we can have a lot of forces on the object, and in this case here we even have 2. So what we'd sort of conclude then is we'd fix this equation up to say, well, a better form of Newton's law isn't F equals ma, it isn't A is F over m, it's better to say it's the sum of the forces divided by m. So if, like in the last example, once again this box here had a mass of 1 kilogram, that was how much stuff the box is made out of, 1 kilogram, we are now free to compute the acceleration on the box. We know if we sum the forces, we get minus 3 newtons, and we know that the mass on the bottom is 1 kilograms, so we know now that the acceleration would be minus 3 meters per second squared. This is the acceleration on the box. And once again, with this acceleration, we're free, say, to predict the new velocity of the box, v is equal to v naught plus a delta t, where this a right here, that a of minus 3 meters per second, would be that a going into there. And of course we can also put it into the x equals dot dot dot, the one that has the 1/2 a delta t squared, where we are also free to take that a and put it in for there. Either way, we have an acceleration, we can predict the new speed, the new position of the box. Where did they come from? Came from forces once again. So we've gone through 3 versions of this law now. F equals ma is not so convenient. A is F over m is closer, but it's still not the best one. This is the best one we have right here. A is the sum of forces divided by m. But, once again, this still isn't really the best form of the law to use. Let me show you why. Let's go back to that box again, or maybe we'll just sort of change it to sort of a ball or something like this. Here's a ball, a top-down view. Let's say one child's pulling on this way once again with a 2 Newton force. This child here just won't give up. And let's say there's another force over here pulling out that way, F2. And let's say, furthermore, we can get a little more technical about it and say there is a horizontal here. Let's say this child is pulling up at 15 degrees, sort of clockwise from the negative x-axis. That's sort of the situation there. So we can sort of run through the Newton's laws version that we have here. We decide that F equals ma doesn't really help us very much. A is sort of buried in there, seems to imply only one force. Looks like this one here doesn't help us much either, because it still implies one force, although A is more accessible to us. We go to the one we just discovered in the last frame here, which says A is the sum of the forces divided by m. Not too useful for us either here, because I'm not really sure how to add forces that aren't sort of on the same axis. This is along the x-axis, this is up at 15 degrees. How do you add those forces together? The other one was easier because they're both along the x-axis. When we had a box like this, and one force is straight over that way, the other force is straight over that way, it was a very simple issue just to add those together. What do you do about the angle? Well, it's not so much that it's difficult as that this law doesn't really help us very much once again. So really what we need to do is, since forces are vectors, we need to say that the acceleration is the sum of the vector forces divided by the mass, and A is even going to be a vector because acceleration can have a direction. But whenever I see a vector equation like that, it's not always so easy to deal with it directly, so what I'm going to do then is break it down into 2 constituent equations, which are probably the best version of the Newton's law that we're going to get here. We can say that A sub x is the sum of the x forces divided by m. And we can say that the y forces are the sum of the y acceleration, the sum of the y forces divided by m. These are probably the best form of Newton's laws that we're going to come up with, and you can see here that it's a far cry from saying just straight up F equals ma. This is not very helpful. This is not a very helpful version of the law. These will be as far as your problem solving goes, even for this one, and let me just show you why. If you go back up to this original figure up here, you can see once again that F1 is pretty easy to deal with. It's all on the x-axis, but F2 over here has two vector components. There's going to be a component this way, and there's going to be a component up like this. Now I'll leave it up to you and your trigonometry to realize that this F2 down here, this is going to be F2 times the cosine of 15, and this is going to be F2 times the sine of 15. These are vector components of F2. So if we want to know how this object is going to move now to get that acceleration once again, we have these forms of Newton's laws which are going to be useful for us. So what we can say then is that a sub x is the sum of the x forces. It's going to be F1 minus F2 times the cosine of 15, all that divided by m. There's our x acceleration. If we wanted the y acceleration, we can get that. Similarly, F1 does not have a y component, so its y component is just going to be 0. It's all on the x-axis. F2 does have a y component up. It's going to be plus F2 times the sine of 15 divided by m. And now we have directly both of our components of the acceleration. So if we want to make some predictions about this object's motion then, we could say something like the new x speed is going to be v naught x plus a sub x delta t, the Gödel equation we've been using. We can make predictions about its position. Remember, x equal to x naught plus dot dot. And remember, there's a 1/2 ax delta t squared term sitting in there. This x acceleration that we got is that a sub x and that a sub x. We can make the same sort of predictions for y motion now too. v naught y plus ay delta t. Or if we want to know where its position is going to be in the vertical sense in the y coordinate, there's a y naught plus dot dot. Remember, there's a 1/2 ay delta t squared in there. So this y acceleration is the same as that y acceleration right there. So the moral here is that most people walk around, they say, yes, I know physics, F equals ma, what else is there? My claim is that, well, F does equal ma, but it's a very unhelpful version of the law. Easy to roll off the tongue, very difficult to use in practice. My claim that it's much better for you to sort of walk around and think that a sub x is the sum of the x forces divided by m, and a sub y is the sum of the y forces divided by m. These forms of Newton's laws are much more useful. They show you a more direct path for problem solving, and I would definitely get those into your head more, walk around saying those things, not this one.